Well, hi. So, obviously, we still ain't got school, so round 2 video. So, last time we talked a lot about the contextual meaning of a derivative, the technical definition, and what it means conceptually. Now let's start talking about how the heck we use derivatives. And this honestly is going to be a lot more example-based and problem-based this time. By the way, welcome to my neighborhood. Here we are in nature. That's a tree. Duh. You can tell it is by the way that it is. We're taking Penny for a walk real quick. Hey, come here. Hi. Scratch your puppy butt. Do you ever feel like a plastic bag? Right, so again, we talked a lot about the definition of a derivative. Talked a lot about what that means, what the slope is, the instantaneous rate of change, all of that stuff. If you don't remember those things, you should definitely go back and watch that. So obviously, derivatives is a really big topic, and there's a lot to cover in there. So I'm going to try and do 4 or 5 really long, extended problems that have a bunch of different parts that are going to hopefully mirror what you are going to see now on the adapted AP test. Speaking of AP test, yeah, it's still happening, and we still got to get ready for it. So here's the deets. Your test is on May 12th at 1 p.m. Central Time. As we said before, everything will be online. If you do not have access to online something, whether it be a laptop or a tablet or anything like that, please let me know ASAP so I can let AP know and we will figure something out. They have that covered, so just let me know if you do not have access to that. There will be 2 total questions. The first question, you're gonna have 25 minutes to answer. It's a free response, and I really don't know what it's gonna look like. They say it's going to look very similar to typical free response questions, but there's no telling what that's going to be. So you have 25 questions on that, or 25 minutes on that question, and then a 5-minute grace period to submit question number 1. Once you are done with question 1 and you submit it, you can never go back to question 1. So make sure whatever you submit is solid and awesome. After question 1, obviously, question number 2. This one, you have 15 minutes to solve it, and then another 5-minute period to submit your answers. Now, you ready for it? It's all online, so this is an open book test. Yikes. Pros, cons. Pros, you have all of your notes. You have the yellow sheet. You have everything at your disposal. Cons, knowing that it's going to be an open note test, it will be different than anything you've ever seen. So conceptually, you are going to have to know exactly what you're doing. That's why I started with that first video of conceptually, here's what a derivative is, and then we'll go into actual word problems and things like that. The questions are written in a way where you do not need a graphing calculator on it, but you can use one if you want to. Also, safe stops are still in. Please, please don't lose points on this weird online AP test because you decided to simplify and you did not need to. Remember, you get to that safe stop, done, box it, and go on. Now, past that, I have no clue. I literally have no idea, which is scary, but we'll get there. That's all I know. That's all AP has said. That's all they said in their last update. Near the end of April, they'll give us a link so we can start signing in and getting used to what this thing is. But again, all you have to worry about, 1 p.m. Central Time, May 12th, open note, 2 questions, 25 minutes, 5-minute grace period, 15 minutes, 5-minute submit period, and you are done. Enough logistics. Let's do some math.
Alright, so welcome to our first question. We're going to take bits and pieces of what derivatives are and sort of throw them all into one cohesive problem and then do another one with different parts and hopefully hit all of the high points. First one is we're going to talk about some of the real basic concepts of derivatives. So I have this piecewise function, g of x, which says from -4 to 0, I have this function. And then from 0 all the way into 5, when we're going to include 5 on this endpoint, it is this weird mix of a linear portion and some trig sine function. So the first thing I want to find out, part A, find the instantaneous rate of change at, let's go, x is equal to -2. Alright, with all of these, if I were you, pause them before I go through them and try them. Get stuck, then come back to it to see what you can do. Pause it. Alright, so instantaneous rate of change. You guys know instantaneous rate of change as my derivative. Remember, I have two ways of really finding derivatives. One of them is this really gross equation, limit as h approaches 0, f of x plus h minus f of x all divided by h, which was the caveman way of doing it, which I sort of don't want. Or we can just, alright, use our chain rule, our power rule, our product rule, or our quotient rule. Quotient. Yay! This one makes Mr. Vinshaw way more happy. Alright, so instantaneous rate of change, that is the derivative. I want to know at x equals -2. Well, what part of the piecewise function is this? It looks like it's this part of the function. So, I want to find the derivative at that point. So I know anytime I have a square root function, I turn it into a power. So this is 16 minus x squared to the 1/2 power. This is going to be a chain rule with a power rule. So the power rule brings the 1/2 down. So this turns into 1/2, parentheses 16 minus x squared, reduce the power. This is going to be the -1/2. Then times the derivative of all the stuff that was on the inside. Derivative of 16 is 0. Derivative of -x squared will be -2x. This 1/2 and this 2 are going to cancel each other out. This -1/2 is going to move all of this business to the bottom, and this lonely x is going to stay up there with the negative. So all told, this is -x divided by square root 16 minus x squared. And this is g prime of x, or at least one part of it. Great, that would be the derivative. I want to find the instantaneous rate of change at this point. Well, all I have to do then to find g prime of -2, plug in -2, so -2 square root 16 minus -2 squared. Now again, this is where I'm saying safe stops. Go ahead and do them. It is all free response. Boom, you're done. Sweet. That's instantaneous rate of change. Sometimes you have seen things like this. Now I want to find the average rate of change and let's go all the way from 0 to x equals 4. I want to find the average rate of change from 0 to 4. Well, again, there should be one clear thing in your head for how we find average rate of change. Average rate of change has always been the same, f of b minus f of a divided by b minus a. Same stinking thing every single time. Alright, technology fought with me, so here we go. We have this average rate of change. We're trying to find f of b, f of a, b minus a. So we got to figure out what our endpoints are. Well, we know one of them at the end is 4. The other one at the beginning is 0. And really it's not f because we're dealing with this function that is already named. So really we should be calling this g of 4. Alright, well let's see where 4 is on this piecewise function. Not in this range. Looks like over here. So this is going to be 4 plus sine pi times 4 over 2. Now let's find g of 0. G of 0, got to figure out where I'm looking, because this is the glue, the seam between these two functions. Well, this one has the equal sign with it, so I'm going to include it on this function and not that function. So my g of 0 will be square root 16 minus 0 squared. That one, pretty easy. Square root of 16, that's going to be a foe. Alright, so all told, our average rate of change is going to be equal to f of b, or g of b. And this, I don't feel like, so I'm just going to leave it like that. So 4 plus sine, the 4 and the 2 will cancel. This will be 2 pi minus the 4 that I got from right here. That's g of 0. All divided by 4 minus 0, so 4. And again, yes, there's some simplifying you could definitely do in there. I don't care. Safe stop. Go on with your life. Be awesome. Do great things. Yup. So the next part I want to talk about, Thoreau's mean value theorem. So I want to find, if possible, the value that satisfies, can't say words, satisfies, mean value theorem over the interval, let's go -4 all the way up to 5. Alright, the thing you should remember about this bad boy, or girl, 2020. We are gender inclusive here. Mean value theorem. If I'm continuous and differentiable, then there exists some value c. So anytime you're finding the value, you're finding the value c, where the instantaneous rate of change, the derivative, is going to be equal to the average rate of change. So basically I'm just throwing the first two parts together into my next. And I want to find where the instantaneous rate of change will be equal to the average rate of change. Well, first off, we got to see if it's continuous and differentiable. Alright, let's look at our function real quick. Let's see if it is continuous. This part right here, well, that's going to be a half circle, so it's going to be continuous pretty much everywhere. This is a linear portion plus sort of trig function. It's going to be continuous, but where I'm worried is at this 0, because at 0 some weird business is happening. So let's see if those two ends actually meet. And the way we're going to do that is we're going to plug in 0 to both of those functions. So coming from the left, because I'm looking at the first function, which is the negative half of it, I plug in 0, 16 minus 0 squared. We've already done this one. We found that that equals 4. Coming from the right, at 0, I'm going to destroy all technology. Help. Okay, so where I was going with that is if I look on the left and I plug in 0, I get a 4, because this is the negative part. If I look at the right, I plug in 0, I get a 0. So what this is saying is at the y-axis, as I'm coming from this side, 4. So I have some squiggly bob function, boom, boom. But when I come up from this side, I have some other squiggly bob function that's over here. And this should be an open circle. So if I'm trying to find the mean value theorem from -4 all the way out here, all the way until positive over here, is this continuous and differentiable? Oh, my chair break. Help! I'm getting fat. Is this continuous? Well, no. I got to jump discontinuity right there. So, MVT does BAM! Alright, trust me, we're getting there. Next part, part D. D's, not going to say the next part, sorry. I want to find the line tangent to g of x at x equals -2. So I want to figure out the tangent line, the linear tangent line at x equals -2. Alright, well again, find tangent. Tangent, we remember, is just derivative. But now I want to find the line tangent. And we've always used one formula to find that line. It's always been our point slope form, which is y minus y1 is equal to m x minus x1, where this m is this bad boy right there. So all we have to do is find the x value, luckily for us it's given, the y value, and the slope. Now, I foresee AP doing something like this on the test, where they give you some other question, can't speak, where they give you some other question that you've already sort of solved. If you go back to part 1, part A, we've already found the derivative at -2. It was this thing. So we've already found our slope. Cha-ching. We've already found our x value. Cha-ching. All we got to do is find our y value. Well, you guys are smart enough to know, okay, if I have an x value, I want to find a y value, I just take this x value, I plug it in. So the function I'm looking at is the left-hand side, because I'm at -2, that's in between -4 and 0. So I'm going to plug in -2. This is going to be 16 minus -2 squared. If you really want to, you can. This is going to be 4. 16 minus 4, I get 12. So this is square root 12. So, all told, my equation is y minus square root 12 equal to my slope, which I found earlier. This is positive 2 over square root 12. I'm just simplifying what we did up here. You could leave it exactly like this if you wanted to, or you could not. That's up to you. Times x plus 2, because it's a minus from the equation and a negative right there. You don't have to rearrange. You don't have to distribute. Say stop that bad boy or girl, and then move on with your life. Alright, the last part on this one, I know. I want to find or approximate the value at, terrible at sign, x equals 1.1. Another way you could see this is approximate g of 1.1. Realize those are saying the exact same thing. Now, anytime we've done approximations, we've had two options. It has either been linear approximations or Euler's method. Now in this case, because we don't have a derivative function, we're not going to use this one. Remember, this one is typically used when we have dy over dx, when we have the derivative. Linear approximation is used when I can take a derivative and then figure out what the approximation is using a tangent line. So really, we're going to retool this same equation we just used, y minus y1 is equal to mx minus x1. We're just going to move this y1 over to the opposite side. So my approximation, y, is approximately equal to the slope times the change in x values plus the y value, which really is Euler's method. I know we've talked about this before, but this basically is Euler's method, where my yn plus 1 is equal to dy over dx, the derivative, times delta x plus your yn. So really the linear approximation and Euler's method are exact same thing. So we just got to figure out what parts and what the heck is going on in here. M, well, that is going to be the slope, and it's the slope at the original point. Okay, well, original point. Yeesh. We're trying to figure out 1.1. What's a good place that I could start at and look forward to 1.1? Well, I say let's start at x equals 1. So I want the slope at 1, and then I'm going to need the y value at 1. I'm going to need all this business. Well, real quick, let's go back to our equations, see which one we're using. This is 1, so it looks like I'm going to be using this one. So the derivative, this is going to be, is approximately equal to the slope, the derivative. I had x, the derivative of x is 1, plus sine, the derivative of sine is cosine of everything that was in there, pi x over 2, times the derivative of the inside stuff, very small chain rule, but don't forget it, derivative of this, well really this is just pi over 2 times x. Pi over 2 is a constant, the derivative of x is 1, so times pi over 2. Now we're looking at the x value of 1, so we'll plug in a 1 in this value. Alright, that represents the slope. Now I need my x value, so this is going to be 1.1 minus 1, because I'm going forward. I want to see where I'm ending up, because you're starting at 1, going forward to 1.1, it's not going to be negative, it's going to be positive. Then plus the y value. Well, the y value, just plug in a 1 into my equation. So remember, my equation was x plus sine pi x over 2. So this is going to be 1 plus sine of pi times 1 over 2. Running out of room. Again, this is a very gross thing, but we're just going to stop it right there. Safe stop, and go on with our life. Alright, I know that was a lot, but to recap, here's our main big ideas. Instantaneous rate of change. That's just the derivative. Average rate of change. That is f of b minus f of a, all divided by b minus a. Mean value theorem, MVT, says I have to be continuous and differentiable. And if that's true, great. Then there's some value c where the instantaneous rate of change, this bad boy, is going to be equal to the average rate of change, this bad boy. Line's tangent. That is where I use my point slope form, y minus y1. is equal to m parentheses x minus x1, and this is the derivative. And then finally, if I'm trying to find a linear approximation, it's the exact same thing as this. The y value is going to be equal to the previous y value plus the slope, which is the derivative, times the change in x. Big key concepts, all related to derivatives.
There's this rule in learning and practicing and studying and all this stuff that says the age you are is basically the minutes that you can retain things. So teachers are told that, okay, 10-year-olds, you go 10 minutes, maybe 12 minutes, and then you give them a little break, and then you keep rotating through that cycle. That was a big, gross, long problem. Take a break. Take a second, go do something else, come back in just a minute. Enjoy dog. Hello, dog.
Alright, round 2. Fight. Jason riding his bike alone because COVID-19 along this straight road. Values for his velocity j of t are given in this table where t is in minutes and j of t is meters per minute. So I got this time and I got his velocity. And apparently this minute he ran into a big dog and freaked out and started going backwards. Help! Here's dog. Boom, boom, boom. Yo. Very cool, Mr. Veenstra. Alright, so some of these I want to sort of circle back to what we did in question number 1, but now see what this looks like if you're given data points, because the process should be very similar, but it's a little bit different, enough so that we need to look at this. So, first off, part A, I want to find the average rate of change from, let's go from t equals 0 to t equals 4. And I want to explain the meaning of this. I want to know what the heck this means for our scenario. Well, again, average rate of change, you should know this by now. F of b minus f of a, all divided by b minus a. Alright, well, we're looking at 4, we're looking at 0, so this is going to be equal to j of 4 minus j of 0, all divided by 4 minus 0. So this is going to be equal to 11 minus 1 divided by 4 minus 0. Alright, so that is 10 over 4. With all of these, make sure you're including units. Up top, looks like we had meters per minute. On bottom, we had minute. So that's the actual average rate of change. Let's talk about what this means for the scenario. I was given a rate. I was given Jason's rate. And I sort of took a weird derivative, the average rate of change, of the rate. So this is saying Jason's rate is changing by this much. 10 over 4 meters per minute per minute. In other words, it's the rate of change of the rate. I'm finding the rate of change of something that was already a rate. And really what this is I was given velocity. I'm just finding acceleration. I found his acceleration. But this is really how you need to phrase this, especially for those AP graders. They love looking at this, saying the rate is changing by this much as I'm going through there. All right, next part. Does there exist a value where the derivative of j is equal to 2.5 from the interval 0 to 4? Anytime you're testing to see if there is a value that exists, there's really only two options. We've talked about one of them. It's mean value theorem. The other one, haven't seen in a while, it's intermediate value theorem. Now you just have to figure out which one deals with a derivative and which one deals with the function. Remember, mean value theorem deals with f prime of c, where intermediate value theorem just looks at f of c. So we want to see the mean value theorem right here. So let's plug our things in. F prime, and really it's not f prime, let's call it by its real name, j prime of some value t is going to be equal to f of b minus f of a, so j of 4 minus j of 0, all divided by 4 minus 0. And then again, here's that example of, hey, AP test might do something where they give you a part of a problem that you've already solved. Now, what we haven't talked about in this is if it is continuous and differentiable. For our sake, we are going to assume, heck yeah. In all AP problems, there will be something in here that tells you, great, j of t is continuous and differentiable. Remember, there is one thing that we talked about in class, that if something is continuous, lies, if something is differentiable, even I got it backwards, that is precluding that is continuous. Because remember, for something to be differentiable, it can't have any sharp turns, it can't have any discontinuities, it can't have any cusps, and it can't go to infinity. Vertical asymptotes. So if something is differentiable, therefore it's continuous. But what I was trying to say earlier, if it's continuous, you can't go backwards and say it's differentiable. But this one, great. Most of the time they'll hide the continuity in there by saying it's differentiable. We know this is equal to 10 over 4. Simplified down, that is going to be equal to 2/5. So yes, there exists some value for t where j prime of t is equal to 2.5 by the mean value theorem. So the sort of ugly step cousin to the mean value theorem is my intermediate value theorem. So part C is asking, could there exist a value where j of t is equal to 0? Now again, if I'm trying to figure out if things exist, most of the time, not always, but most of the time it's either going to be MVT or IVT. MVT deals with derivatives, IVT deals with functions. Remember, IVT just says, great, if I'm continuous, if I go from, let's say, 1 to 8, and I'm going continuously through there, that means I have to hit every single number in between 1 and 8. There's no way I could get from 1 to 8 if I'm moving continuously and not hit every single thing in between. So, we want to see if I can equal 0. From 1 to 8, I don't really know. I could go up and down. There's not a lot of information, so I couldn't say there. 8 to 1.5, I could go up and down. Nothing there. 1.5 to negative 5. The only way I could get from a positive number into the negative numbers is if I passed through 0. So yeah, there's one place. It's right in between 2 and 3. Then again, I go from -5 way up to +11 as I'm running away from Jason's dog. So there's another place right there. So, yes. Woo! By IVT, there exists 2 points where j of t equal to 0. Oh, crooked. Now notice it's not asking me where. It's just asking, okay, does there exist? Okay, cool. Yeah, there's 2 of them. If it asked where it would exist, it would happen between 2 and 3 and between 3 and 4. Oh my goodness, this is so much math, I'm dying. Help! Alright, somehow we figured out that Jason's velocity is now following this function. Who would have thought? I want to find the min and max of velocity. Oh boy, here's something that hasn't popped in a hot second. Mins and maxes. Remember, you have to find the critical point. Critical points are where the derivative is equal to 0 or undefined. And then you have to see where f prime changes signs. Sings. Help. Changes signs. Now for our case, we're going to look at the closed interval 0 to 4. And hopefully that sort of lights a fire in your brain and says, oh, okay, wait, there's something going on here. Not only do I have to do this, I have to do something at the end as well. But we'll get to it. So, if I'm finding the min and max of velocity, I first need to take the derivative of the velocity function. Derivative of velocity, this is going to be 1.5, bring down that to x. Derivative of x is just 1, so minus 4.5. Derivative of 4.5 is 0. So this all told is 3x minus 4.5. Let's set it equal to 0, figure out where the heck that is. 4.5, move it over, so this is 3x, 4.5, divide by 3, divide by 3, and I believe when you type this in your calculator you get x is equal to 1.5. So this is my critical point. Doesn't mean jack nothing for anything about mins or maxes. So I'm starting at 0, going all the way to 4, and I have 1.5 in the middle. So let's test the innards of this. Let's pick a number between 0 and 1.5. Let's try 1. Plug a 1 into my derivative equation. So if I have 3 times 1 minus 4.5, that means that the derivative is going to be negative there. Let's try something over here. Let's try 2. So 3 times 2 minus 4.5. 6 minus 4.5, that's definitely going to be positive. The derivative is negative right here, meaning my function, my velocity is decreasing, decreasing, decreasing. The derivative is positive over here, which means my function is increasing, increasing, increasing. Meaning at 1.5, I have a minimum. Now notice how I asked the question. I said find the minimum velocity. So the actual minimum velocity, I have to take that 1.5, plug it back in. So this is 1.5 times where my minimum happens is at 1.5 squared minus 4.5 times 1.5 plus 4.5. This is, let me go off to the side here, my minimum velocity. Now, I still have to find a maximum and see if it exists. Well, I gotta test my endpoints because I'm starting at 0 and then I'm decreasing away from it, meaning that this is a maximum, and then I'm increasing all the way up into 4, which means it's also a maximum. All I have to see is which one is actually bigger. So I'm going to take 0 and 4, plug it into my calculator real quick. Scoop, boop, boop. This is called a calculator, in case you have forgotten what these look like. 1.5 times 0, and really I don't need to do the 0 case, so let's start with the 4. 4 squared, what was my equation? Minus 4.5 times 1. No, we're doing 4. I can't type. Then plus 4.5. So the velocity at the end was 10.5. If I plugged in a 0 in there, this is what I was saying by you don't really need a 0. This will all cancel. This will all cancel. So you're just left with 4.5. So my beginning velocity is 4.5. My ending velocity is 10.5. It's looking like the end point out here is going to be my maximum. So my max velocity happens at 4, and that is equal to 10.5. Now let's put units on this just to make sure. Meters per minute, meters per minute. And we are golden. Chicka-blow! Alright, the last little topic I want to throw in here is sort of not relating to the problem that I've been writing. It is just to incorporate one small facet of derivatives, and it's going to take a little bit to get there because I'm seeing a limit right here, but hopefully you know where this is going. I want to evaluate this limit. Well, same thing I always do with limits. I have to plug in things to the top, plug in things to the bottom separately. So this is the limit as t approaches 0 of 4.5 minus v of t divided by the limit t approaches 0 of e 3x minus 1. Alright, so let's do the first one. That's going to be 4.5 minus v of 0. Now I'm still using Jason's speed. It just sort of has no contextual meaning in this problem. This is meaning I want his velocity given that equation I had at 0. Again, I've already found it at 0. We plugged it into our calculator and we found that v of 0 was 4.5. So this is 4.5 minus 4.5. So it's going to be 0. Oh boy, I think I know where this is going. The bottom will evaluate to, this is going to be E3 times 0 minus 1. Remember your small little algebra tricks. This is 3 times 0, which is 0. E to the 0 power, anything to the 0 power is going to be 1. 1 minus 1 will also be 0. And would you look at that? Would you just look at it? We know what we do when we get to this. Gonna hop on over there. Use L'Hopital's. And so remember what L'Hopital said was if I get an indeterminate form, either 0 over 0 or infinity over infinity, I can just redo the limit. Oh no, I have the Rona. By taking the derivative of the top, derivative of 4.5 is 0, derivative of v of t is going to be v prime of t. Don't forget that little negative because of the minus sign. And take the derivative of the bottom. Notice this is absolutely not quotient rule, it's just derivative of top, derivative of bottom. Derivative of e to the x would normally just be e to the x, but because there's something there, it would be e to the 3x times the derivative of whatever was up there. Derivative of 3x is 3. Derivative of 1 is 0. Alright, so I can reevaluate this limit. This is the limit t approaches infinity of negative v prime of t, all divided by limit t approaches infinity, or not 0, 0, not infinity, yikes, of 3e to the 3x. Let's do the top first. This is negative v prime of 0. Well, that's the derivative at 0. I don't think I've done that one yet. The derivative function should have been, let me look back because I forgot to. My derivative function is this 3x minus 4.5. So this is going to be 3 times 0 minus 4.5. All divided by, figure out what's going on the bottom, 3 e3 0. Well, again, e to the 0 is going to be 1 times 3 is going to be 3. So all told, this limit is negative 4.5. No, actually, not negative. Lies! I left out a negative up here. Yikes! So negative will turn into positive divided by 3. And that is my limit. Don't panic because it's a fraction within a decimal or a decimal within a fraction. That okay.
Yeah, even I'm starting to get a little drained. So, again, one more break. We're going to only have one more problem. It's going to deal with some implicit differentiation. I'm going to go make some dinner, and then we'll get back to this. Deuces. I mean, my dog's going to go eat because my salmon fillets have not thawed. So I'm just going to charge through, and we're going to get this done. But no promises on how great the math is because, yeah, dog.
Alright, last problem. Here we go. We're still doing more derivatives. There's a couple things I'm not going to hit in this video, but that is okay. I will tell you what to do, and we will go from there. Ooh, you suck. So let's look at a function. Our function is 3x squared plus 4y squared minus 6y is equal to 10. Now, right off the bat, you can tell this function, Slim Shady, is a little bit different because it's not y equals stuff. I got x's and y's all together on one side, and we had a name for that. This was called implicit. It is an implicitly defined function because I have x and y's together, and it's not explicit. Remember, explicit is y equals in terms of one variable. So first thing I want to do, let's find dy dx. Alright, dy dx, cool. I know that symbol. Well, that's just a derivative. Hip. If anyone can tell me what that quote is from, or what's attempt to be from. I can't read. Hip. I think I've actually told you that one, so never mind. It's not that impressive if you know. I want to take the derivative of all this business, and there was a certain way we did this when we had implicit differentiation. I'm taking the derivative with respect to x. Oh, puppy's done eating. Yay. 3x squared plus 4y squared minus 6y equal to 10. And I'm just going to go term by term and take the derivative. Alright, so let's look at this one. I'm taking an x term with respect to x, so nothing fancy happens there. Bring the power down. 3 times, ooh, voice crack, yep, that's 1. 3 times 2 is 6. The derivative of x with respect to x is just 1, so it stays like that. Now look at the next one. Plus, derivative of this, I use my power rule, so 8y. The derivative of this variable, however, with respect to x, is not going to be 1. That is times dy dx. That's a small chain rule because I'm taking the derivative of a different variable with respect to x. Not just x and x, but y and x. So I get a dy dx in there. Minus derivative of 6y would just be 6, but the derivative of y with respect to x is dy dx. Derivative of 10, well, yeah, that's just 0. Golden. Alright, I don't have dy dx by itself yet. I have all this stuff. I don't have dy dx is equal to this. So let's move the 6x over. 8y times dy over dx minus 6 dy over dx is equal to negative 6x. Now, I see that both of these terms have a dy over dx. I can't get the dy dx by itself until it is multiplied. So let me factor it out. dy over dx, parentheses 8y minus 6, is equal to negative 6x. And now this is pretty decent. I can divide this across because this is multiplied. Now this is isolated. So dy over dx is equal to negative 6x over 8y minus 6. Boom, blam, 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 bam. Well, the next part, let's go even deeper into this maze. I want to find d squared y dx squared. Oh boy, let's just panic and give up. Because sadness. No, let's not do that. D squared y dx squared, that's just a fancy way of saying, okay, well, let's find the second derivative. I want to find the second derivative. Well, I already found the first derivative. Second derivative, I just need to take the derivative of that. So my first derivative was dy over dx is equal to negative 6x 8y minus 6. I need to take the derivative of this. Well, warning, danger, danger, danger. This is division. And when I'm doing division, I need a quotient rule. So, my quotient rule, if you have forgotten, our memory hook, low times the derivative of the high function minus the high function, the top function, times the derivative of the low function, all divided by the low function squared. So, let's use that memory hook, see if we can take the derivative of this. D squared y dx squared. Apparently there's a motorcycle gang going past my house right now. I'm in danger. The low function, which is 8y minus 6. Oh, they're coming literally in our driveway. Interesting. Times the derivative of the high function. If I get murked. Goodbye, children. Negative 6. Minus the high function. Negative 6x. Times the derivative of the low function. Derivative of 8y is just 8, but I'm taking the derivative with respect to x, so it's going to be 8 dy dx, and the derivative of 6 is just 0. All divided by 2a. No. All divided by the low function squared. Yikes. This would not be a safe stop. The only reason it is not a safe stop is because of that dy dx business. I will always want this d squared y dx squared in terms of x and y. And right now it's in terms of y, x, and then another separate variable. Well, luckily for us, we already found what that separate variable is right here. So I can sort of just plug that in and go from there. Ooh, I'm really hungry. So this is negative 6, 8y minus 6. We can combine that. That's going to be plus 6x times 8 times whatever my dy dx thing was, which is this gross fraction. Negative 6x, 8y minus 6. Close off all those parentheses. And divided by 8y minus 6 squared. Now that is totally a safe step. And I really don't want to do the rest of the algebra to get anywhere past that. Alright, we're still going strong. Next part, I want to find the y value for all vertical tangents. Oh boy. Vertical tangent lines. Remember, vertical tangent lines are tangent lines that are going straight up and down. In other words, they have a slope that is undefined. Undefined slopes happen where the numerator is equal to 0 of a fraction. The opposite case of this, which you should definitely know, are vertical tangent lines. This has a slope equal to 0, and that's where in a fraction the numerator is equal to 0. So undefined slope is where the denominator is equal to 0. That is a vertical tangent line. Horizontal tangent lines, slope is equal to 0, slope where the numerator is equal to 0. So if I want a vertical tangent line, I want to see where the denominator of the derivative, because I'm looking for tangents, is equal to 0. Alright, well, let me take my derivative function, which is this that I found right up here. Negative 6x, 8y minus 6. And let's set the bottom equal to 0. So 8y minus 6 equal to 0. Because if this entire thing is 0, it'll make an undefined slope. So 8y equals 6, y is equal to 6 over 8. And boom, that one was easy. I put this in here to hopefully illustrate to you that, yeah, you might run into some really easy problems on this. Again, I have no clue, but if it's anything like they're saying it's going to be, and it's similar to normal AP test, don't panic if you get something that's like, oh, okay, cool, I found it, and I can move on. So last one in this one, we're not going to go to 5 parts on this one, just do this last part. I threw in an Euler's method problem on this to sort of show you the similarities of what we talked about earlier with a linear approximation and an Euler's method. So we're assuming that when y is equal to 2, x is equal, or when x is equal to 0, y is equal to 2, use dependent, independent. Approximate the y value when x is equal to 0.4 using Euler's method in 2 even step sizes. So remember, Euler's method is a stepwise approach using the derivative and tangents to figure out and approximate different values. We have our next x value is equal to our previous x value, or xn, sorry, plus delta x. And our next y value is equal to our previous y value plus the derivative times delta x. Now this derivative is at the previous point. It's a big thing that we used to mess up when we were doing this Euler's method business. So I'm starting at 0. I want to go to 0.4. If I'm using 2 even steps, even if you forget or you're just lacking common sense, 0.4 minus 0 divided by 2, that means each step size is going to be 0.2. That is my delta x. Alright, so the first step, my next x value is going to be 0, my previous x value, plus my delta x, 0.2. So that's going to be 0.2. Yikes, that's pretty simple. My next y value is going to be equal to my previous y value, 2, plus the derivative, which remember my derivative equation is this bad boy right here, at the previous point. So, wait, I forgot a game. Negative 6 times the x value previous, which was 0, divided by 8y minus 6 times my delta x, which is 0.2. And in this case, yeah, I'm probably going to need to use my calculator. So me go in there. 2 plus, let me just do this. 0. Oh no, it's a 0! Lies! Ha 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 ha! I did make something nice. See, I thought I did. So negative 6 times 0 is going to be 0. Doesn't matter what this is. It's going to be all 0. So this is still equal to 2. So on my first step, nothing changed. My y value stayed the same. Now I'm going to do one more step, because I think that will get me to where I'm going. Delta x plus the previous x value. I'm now at 0.4. Yay! That's where I wanted to be. Then my next y value is equal to my previous y value, which was still 2 in this case, plus the derivative at the previous point. So now my x is 0.2, because it was 0.2 right here, divided by 8 times my previous y value, boom, 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 times my delta x. And this one, yeah, I'll definitely want a calculator for. So I have negative 6 times 0.2 divided by 16 minus 6. Really didn't need to do that. Hello, cosine. I don't know where you came from. Delete! Negative 0.12. Multiply that by my delta x. Add it with 2. And there is my approximation. This is a good point to remind you. Always use 3 decimals. And you can round or truncate. I don't think that'll be an issue on this test, but if it is, then there you go. Remember, approximation needs a little tilde, boys. 976. Oh my glob. Boom!
Yikes. That was a lot. So for the most part, that is all of derivatives. That goes through mean value theorem, how to use derivatives, technical applications of derivatives. There are 2 things I did not mention. Related rates, yikes, and concavity. I will find somewhere to get in there, concavity and maybe a little bit of related rates. But for the most part, what we focused on is the main bulk of the review that I am going to do with you. So, yeah. If you haven't heard through the grapevine, we are starting to take grades now. So, for me specifically, and you guys in calculus, I'm going to be extremely, extremely lenient. You should not have to panic during a time like this about getting grades in a class like this. What I want you focused on is the review, going through these videos, and trying some things on the AP Classroom. I will send out something that will be counted as a grade, but don't panic. It will not be super heavy math intensive. What it'll likely be is some Google form saying, hey, you alive? Click yes or no. Do you like Skittles? Yes or no? Great. You have a grade now. And again, the reason being is, for the most part, I know all of you are doing exactly what I'm asking you to do. You still have this AP test coming up. You can still do this. This is not a lost cause by any stretch of the imagination. And we're doing that. You've got these videos. You've got the AP Classroom. And you have me. If you have questions, send emails. Let me know. As always, I love you guys. I miss you like crazy. If you ever just need to reach out and see how my day is going, or want to talk about your day, or literally anything, shoot me an email. We can talk. Check out something for the Zoom. I don't know when we're going to do that, but I'm trying to get that working, trying to see what I can actually do. Other than that, stay safe, stay awesome. You guys are great. I love you. I miss you. Deuces.